the fact that the chemical potential takes on this form where you have a piece that has to do with any internal degrees of freedom and how that solute interacts with the solvent that was wrapped up into what we called the standard state chemical potential, and a piece that was isolating all of its density dependence. And so we found out a lot of consequences of that form. And now we're trying to understand a little more deeply what sets that standard state chemical potential. And in a specific set of solute-solvent interactions, there's some very general things we can say. And specifically, we can say some things associated with how charged solutes are solvated by polar solvents. And so the theory we're going to try to build towards is a theory for ionic solvation. And to get there, essentially today we need to take a step back and really just review some basics of electrostatics, and things you probably forgot from that physics class you took long ago. But now, this lecture will kind of give a one lecture summary of what is a large complicated field of electrostatics. I've, in addition, posted with this lecture a set of notes that my colleague Phil Geisler wrote specifically for this class, which are, I think, very useful. So you can refer back to those as well. They're relatively self-contained. Okay, so to start considering questions in electrostatics, everything really builds off of kind of the most basic statement one can consider, which is how two charges interact with each other. So let's do that. Let's consider two charges with charge Z1 and Z2, both greater than 0, separated by a distance r. And I'll denote distance as the modulus of some displacement vector r. So if we wanted a picture, there's the position of, say, Z1. There's the position of charge Z2. They are separated by some vector, r vector. Now, from Coulomb, we know that the force on particle 2, charge 2, force is also a vector. If we care only about its magnitude, it depends on the separation distance squared. And so for notation, I will, when I write r without a vector, implicitly mean the modulus. This is the so-called inverse squared law. As the charges get farther and farther apart, that force acting on each individual charge goes down in proportion. We also know from Newton's third law that forces are equal and opposite. So if I ask for the force on particle 1, that's minus that, the force on particle 2. And Coulomb told us that the specific form of that force depends on the magnitude of those charges, some fundamental constants, and that proportionality, the squared distance. Now, force is indeed a vector, so we need both a magnitude, what we've just written down, and a direction. We'll denote that direction r hat, where r hat is the so-called unit vector. It has norm 1 and points in some direction. So we can actually draw those force lines. So if 1 is separated by 2 in this direction, it exerts a force on 2. If both of those charges are positive, that acts to repel 2 from 1. And similarly, 2 exerts a force on 1 that acts to push it away. So the force on 1 would look something like that. So that's how the forces on charges would look. This needs to be parallel. Let me draw that a little more carefully. Okay. Now we also know from mechanics that forces are derived as derivatives of potentials. That is to say that if we knew the potential of a system of charges and how it depends on their distance, for example, we could compute those forces. Or as a consequence, if we knew the force, we could integrate to find the potential. Integrating that force gives us a potential of those two charges, u of r, which depends only on their separation distance, and has a form that now goes proportional to 1 over that separation distance. A potential energy is a scalar. It doesn't depend on the vectorial nature of that displacement vector, just its magnitude. Again, the force then is the gradient of that potential in 3 dimensions, which we've just worked out or asserted. Takes the form of the inverse square law with this normal vector. These two together are what we'll refer to as Coulomb's law. So equivalent statements of either what the potential of two ions are or their corresponding force. Right? And from this law, everything else can be derived. And so essentially what we're going to do is understand some consequences and some implications of just this Coulomb's law, how two charges interact. For simplicity, what we're going to do is write this in a slightly more compact way. We're going to absorb, for everything that I'll denote today, the factor of the fundamental constants 4 pi epsilon naught into my definition of a charge, such that Qi will be Zi divided by square root of 4 pi epsilon naught, so that the potential can be written a little more simply as Qi Qj over R, and similarly the force is Qi Qj R squared in that direction of R. Now, the first thing to note is that the Coulomb potential, this potential that goes like 1 over R, it's what we would call long range. It acts over really large distances. And that's because it decays much more slowly than other typical interparticle interactions. For example, dispersion interactions or other ways that particles might interact, or through hydrogen bonds, etc. What we mean by this is if I was going to plot U of R versus R, that a dispersion interaction it scales with distance as 1 over r to the 6th, so I don't have to go too far before its magnitude is essentially 0. Whereas Coulomb interactions maybe let me give the dispersion a different color. Whereas Coulomb interactions, because they decay like 1 over r, say for like charges where they're attractive, I have to go to much further distances, separation distances, to get a comparably small attractive potential. So that is to say that typical non-charged interactions like dispersion forces decay very quickly as I separate species, whereas Coulomb potentials interact over really large distances. And there's some really important consequences that make charged interactions fundamentally different from their dispersive counterparts. And a nice way to see that is to imagine a collection say of n charges that are identical. Let's call them ions. Let's say that they each have charge Q. And I'm going to put them in a macroscopic box. That has volume L cubed. So here's our box. We have charges. All with the same magnitude of charge as Q. Well, for simplicity, imagine that that's a positive sign, so that Q is greater than 0. Let's go ahead and imagine that this one here is ion number 1. We'll label that one, but they're all identical. And let's ask a very simple mechanical question, which is, in such a system, what is the potential energy? Well, the potential energy, on average, these charges move around, so the potential is a fluctuating quantity. We can ask for it on average under conditions of thermodynamic equilibrium. Well, whatever that potential is, it's going to be the same for all of those ions because they're all statistically identical. So I can write down the average potential of the whole system as N times the average potential on particle 1 divided by 2. I'll divide by 2 in order to not overcount the interactions between particle 1 and particle 2 as distinct from interactions between particle 2 and particle 1. So this thing I'll define as the interaction between ion 1 and all others. Now, the potential energy is a quantity we would expect to be extensive. It should increase in proportion to the scale of the system. That scale is set by this factor of n out in front, which means that for U, the potential energy, to be intensive, we would expect that U1 should be intensive. Okay, so let's try to compute it. So for simplicity, let's imagine that this ion number 1 is fixed at the origin. If all places in this volume are statistically equivalent, we can fix one particle at the origin without changing any physical properties of the system. That essentially sets up our unit, our coordinate system. So if ion 1 is at the origin, I can compute its potential by summing over all of the other particles, which will go from 2 to n. And Coulomb's law tells me what the potential of a pair of ions are. If the ions have the same charge, it will be q squared, and the displacement between those two charges, if one is at the origin, then just depends on where particle I is. On average, the potential of ion number 1 then is just a sum over all the other charges. If all the other charges are also indistinguishable, I need only to compute one of those terms in the sum in order to have all of the potential on particle 1. Now I'm going to rewrite how I'm going to do that sum. So that average depends only on where particle I is. And I is any particle I from 2 to n are the same. So instead of looking where particle 1 is or particle 2 is on average relative to particle 1, I can ask where all of the particles are equal, where all of the particles are likely to be. So if I know the probability of any particle being at a specific point, instead of summing over all the particles, I can sum over all of those points. That is saying that I can turn the sum over particles into an integral over positions. Now the particle positions are not changing, just where they are likely to be. Where they're likely to be is given by some density that depends on R1 being at the origin. So this is just the average number of ions at a given position, provided number 1 is at the origin. So again, all the particles are indistinguishable. The average potential on 1 just depends on where the particles are, the other particles are. And so I can rewrite that sum over particles as a sum over places that they can be, times essentially the probability that they could be at one of those specific places. Now that is a quantity, that density, average number of ions at a given place, which we have some expectations for what it might look like. We'd expect that if I was to plot that average, say a function of displacement, so if those particles are a fluid, if they're rotationally invariant, if every direction I look at, I see the same thing on average, then that density shouldn't depend on the direction I point in, just how far away from the origin I am. Now remember, I placed particle 1 at the origin, so the probability that I see another particle at the origin should be 0, because that first particle is going to exclude some volume. If we say that sigma is the ion size, that we know that because that ion is going to take up space, we know that another ion can't be on top of it, so that density at the origin up to some size sigma should be 0. Now we also know that at really far distances away, if I went a macroscopic distance away from the ion, away from the origin, that the probability to find a particle at any specific point should be uniform and just given by the density, just however many particles I have in that volume. So at some macroscopic distance away from the origin, let's call D, I should expect the density, the likelihood that a particle is at any given point, to be equally likely. Now, in between that molecular size and that molecular distance D, where the particles forget that the ion number 1 was at the origin, there's probably some complicated profile that tells me how that density changes. Might depend on the details of what the shapes and sizes of those ions are and what the density of the total number of ions are. We're assuming that the density is fairly dilute. But if this is our expectation, that's how we expect that density to look like, we can write down the average potential on particle 1 as being q squared, and we can break this up into 2 different integrals. An integral where that density is constant, which is true from D to whatever our macroscopic volume is. I could integrate over all the angles, gives me 4 pi. Spherical coordinates gives me r squared. That potential was 1 over r. And a piece that integrates from 0 to D with the same spherical coordinate pieces, whatever that density is over 0 to D, and then my Coulomb potential again. Let's call this first part U far, for acting on distances far away from the tagged ion number 1. In this piece here, U near. The detailed, depending on the detailed way ions arrange themselves near the origin. So the first integral we can do, that's just an integral of r, just an integral over r, that gives us 4 pi q squared rho bar over 2 L squared, that's the top part of that integrand, minus D squared, that's the bottom part of that integrand. And in general, we have some average thermally of U near. Now let's make some simplifications. So right at this point, we've not made really any assumption. We've just said that if I look far enough away from the ion at the origin, the density should be uniform. I should forget about the fact that the ion number 1 was at the origin. That is saying that there's a length scale over which the density is correlated. The other ions know about the tagged ion. And beyond that, the likelihood that the ion is at any given point in space is equally likely. Now let's assume that d is a microscopic distance, or at least that that the range over which the positions of ions are correlated are much, much less than L, such that when I square d and squared L, I can neglect that term. Similarly, if d is microscopic, this term is microscopic. All of U near boils down to some small energy relative to something that goes like this macroscopic distance L squared. So to a good approximation, we find that the interaction potential of particle 1 due to the other ions is proportional to L squared, this macroscopic distance, this macroscopic length. If I fix the volume and the number of particles at a constant, thus setting a constant density, the fact that U goes like L squared implies that U scales with the total number of particles to the 2/3, because at fixed density, N is proportional to L cubed. Just saying that at fixed density, I can't independently change the number of particles and the volume. That says that the interaction energy of particle 1 depends on the macroscopic size of the system. It depends on how many particles are in that system. That's a real problem. That implies that U1 is not intensive. It depends on the scale of the system. It implies that the total potential, which is a factor of N times the potential of ion number 1, scales like N to the 5/3, which is not extensive. The potential energy continues to increase superlinearly as I increase the scale of the system. This is a real problem. If L and N increase, and there's a relationship between the potential and the number of particles, which is not extensive, that implies that typical intensive quantities, like the pressure, would not be intensive, and rather they would also increase with the size of the system, which means that the pressure, as L and N become large, would diverge. Oh boy, this is a real problem. We've just put a box of ion, in this box a set of ions with the same charge, and we found that that is so unstable, the pressure would build up to something, making it completely unstable. We've essentially made a little bomb by trying to fill a whole bunch of ions into one box. So what on earth did we go wrong? What on earth happened? Where did we go wrong? Where did we go wrong? You all know, let's take a step back. What did we just do? We took a macroscopic volume and filled it with ions of the same charge. Now, can we actually do that? Could you physically prepare such a volume? No, absolutely not. We can't have ions without counter ions to balance out that charge. Namely, if we were to take our macroscopic volume and sum over all the charge, we have to have something which is really close to zero. Something much, much less than Avogadro's number. This is a condition of charge neutrality. Essentially, this comes about because those interactions decay so slowly. This integral we did here for mu far, it gave us something dependent on the macroscopic length because 1 over r can't compete with how the volume elements increase as I increase r. If I only divide by one factor of r, that Jacobian r squared keeps increasing. If I put dispersion interactions there, 1 over r to the 6th, that would be an integral which converges. It doesn't depend on the upper bound of that integrand. So the long-range interactions from Coulomb's law imply this factor of charge neutrality, this constraint of charge neutrality. If I really do try to put particles in boxes that all have the same charge, the fact that they interact over such large scales means that that system would be unstable. Only systems that have net neutral charges won't have this problem of having infinite pressures being completely thermodynamically unstable. That isn't to say that one can't create boxes with a few charges in them. The pressure would be large, but not macroscopic. In fact, people around the chemistry department and in the physics department all the time produce individually charged species out in the vacuum, say. And if those charges number in the tens, then that system is thermodynamically stable. The pressure can be large, but it's not unstable. It's only if I try to generate a macroscopic number, oh, bless me, excuse me, a macroscopic number of same ions without their counter ions, will that system become unstable? Again, a consequence of the long-range nature of those interactions. That's a useful thing to keep in mind. So we've discussed individual charges. There's another object in electrostatics which is going to be very relevant for our discussion of solvation, and that's to introduce the concept of a dipole. A dipole is just what happens when you separate charge over a small distance. So if we imagine some little amount of charge A plus, separated by some amount of charge A minus, and that distance separating them, let's call capital R. If that capital R is very small relative to, say, how close other charges are to the charge A or A minus, we can denote that object as a dipole and give it the symbol M, vector because it depends on the direction that the positive charge is in relationship to the negative charge. The modulus of that dipole is just the amount of charge which is separated times that displacement distance for r small. That's useful because quite often we're dealing with molecules that don't have net charge, they aren't ions, and yet there might be some amount of charge localized in one part of that molecule and some amount of countercharge localized in another part of that molecule. Take, for example, a molecule of water. The hydrogens are a little more positive than the oxygen is a little more negative. So it separates charge locally over the scale of the molecule. That's why we would say that water has a dipole moment. It has a small amount of charge separated over a small distance. It behooves us then to think about how dipoles interact with charges. So if I have a charge Q here, separated from a dipole that has both extent and direction. So there's a dipole M, again, which is just a little bit of positive charge separated from a little bit of negative charge. Let's call that separation between the charge and the ion R vector. The potential energy between that charge and dipole can be written out, and it depends on the magnitude of the charge, the magnitude and direction of the dipole decays like r squared and depends on the direction that dipole points in relationship to that displacement vector r. So I take the so-called dot product between the displacement vector r and the vector m dipole, multiply that by q and divide by r squared. That gives me the potential. You could arrive at this result by writing down the Coulomb's law between both of those small charges on the dipole and taking that limit where they're separated over a small distance relative to the modulus of r vector, little r vector. You can understand why this dot product looks the way that it does by thinking about, well, if that dipole oriented itself parallel to the displacement vector, I will have moved that negative charge a little bit closer to the charge Q, moved the positive charge a little further away from the charge Q. If Q is positive, that would give me a more favorable potential. If the direction of the dipole is perpendicular to the displacement, well, then the positive and negative charges are equidistant to the charge ion on the ion. That gives me a net zero potential because I have a positive potential that exactly cancels out a negative potential. So that's how dipoles and charges interact. I also will need to know how dipoles interact with each other. Let's say I have two dipoles, M and M prime, again, both vector quantities. Let's put one dipole here. Let's put another dipole here. They have some separation vector. The interaction potential between those two dipoles, you can kind of see the pattern. Coulomb's law, the potential goes like 1 over r. Interaction between charges and dipoles goes like 1 over r squared. The interaction between two dipoles goes like 1 over r cubed. And it depends on the relative orientation between those two dipoles. Again, a little bit of negative charge, a little bit of positive charge on each. If they're oriented parallel to each other, the positive charge will be a little bit closer to the negative charge. That should be favorable. But it depends on the relative displacement vector. So I need to, in addition, dot those into each other. So that's a bit complicated, again, derivable from working with this explicit set of charges that make up the dipole, and then taking a limit where they're separated over a distance smaller than their displacement distance. Okay, so there's one last quantity that's set of quantities which is useful to bring up in a discussion of electrostatics. And that, these quantities are useful when I have a collection of charges. Those two quantities are known as electric potentials and electric fields. Again, they are shorthand quantities that concisely summarize whole electrostatic environments when I have a collection of charged species. So let's imagine then I have some box, and in that box I have lots of different charges. I know that if it's a macroscopic box, I need to have an equal number of positive and negative charges. But let's imagine in a specific region, place a test charge with magnitude Q is equal to 1. So I fix the positions of all the ions at some instant in time, and then at some position in that system, I imagine putting down a little imaginary charge with charge Q is equal to 1 and asking the question, what is the potential on that test charge? And the force that would act on that charge. The electrostatic potential is a concise way of addressing the first question. What is the potential at that point in space? We'll denote it phi, depends on where I put that test charge, and is defined as the potential energy that that test charge would feel. So again, that is a concise way of asking about the total system, because that potential is going to depend on all of the other ions. I need to sum over the potential that that charge would feel due to the charges everywhere else. And so if all of the other charges are in that sum over I is 1 to say I have in charges, the potential from that specific ith charge is given by Coulomb's law. It just depends on the magnitude of its charge over the separation distance between where that ith charge is and the particular position r that I'm asking for that potential at. So that's the electrostatic potential. The electrostatic field, or the electric field, we'll denote c. It is a vector, and then just addresses the second question, which is what is the force on that test charge? So as always, we can compute the force from a potential by taking its gradient. So if I know the potential energy per charge, per test charge, I can compute the field by saying how does that potential vary in space by taking that gradient. If I'm in 3 dimensions, the gradient is just d dx, d dy, d dz. So it will have 3 components. The electric field has a direction in 3-dimensional space and some magnitude. Electric fields are particularly useful because they let us think about how, another way of thinking about interactions between charged objects like charge and dipoles. So that is to say that it turns out the charge dipole interaction can be written as, so the potential between a charge Q, ion M, dipole M, can be written as the electric field generated by that charge dotted into the dipole. That gives you some intuition for how dipoles interact with charges. I'll get the most favorable interaction if the direction that dipole points is in the same direction as the field the ion generates, which tells us that dipoles tend to align in electric fields. To give you some a little more understanding of electric fields, we can draw out what some electric fields look like for simple objects. Say by a point charge. So let's imagine we have some charge Q. The electric field is the force that a test charge would feel due to that ion. If Q is positive and the test charge is defined as positive, and if I put a test charge here, say, at the very beginning of lecture, we said that the force due to Q on that charge would be repulsive. So it would, given some displacement in the northern direction, the electric field due to the test charge there would be to push it further away in that same direction. Similarly, if I place a test charge just below charge Q, I would feel a repulsive potential that pushed me further south. And so you can generalize that to all directions. So the field due to an ion is kind of simple. It just looks like this radial set of vectors emanating away from that origin. Actually, let's put this here. Say that would be the field, electric field generated by an ion. It's a little more complicated that I'll post, but one could ask for what is the potential or the electric field generated by a dipole. So let's imagine that I put the dipole pointed in that direction, pointing north. And again, if I think about what the dipole is just being a little bit of positive charge separated from a little bit of negative charge, at the positive end, I'll look just like the electric field generated from that positive charge right above us. So I have field lines that emanate radially away from that northern part of the dipole. On the opposite end of the dipole, however, I have a negative charge. So the lines look like they do from the positive charge, except for they're pointed in the opposite direction. So instead of diverging away from the dipole, they'll converge towards the dipole. And now those lines have to be continuous, which means that they have to come back on each other. So the field lines of a dipole have this kind of complicated vortex-like structure. It's useful, again, to have some intuition or think through what these lines look like, because if we were to put, say, a charge in that dipole field, by knowing what those lines look like, we would have some intuition for how that charge would move. Similarly, if we think about putting two dipoles together, the fact that those field lines emanate in that way would give us some intuition for how the dipoles would want to align. Imagine trying to put a dipole right underneath the dipole we've just drawn. How would it like to point? What about if it was next to it, just on its side? Would it like to point in the same direction? We've said dipoles like to align in the direction of the electric field. So indeed, if another dipole was side by side, if two dipoles were side by side, they would want to point anti-parallel to each other because those fields curl up the way that they do. Whereas if they were right underneath, vertically distributed, they would want to be parallel to each other. Indeed, that's what that interaction energy we wrote between two dipoles would suggest as well, this form here. Okay, so that's all I really had to say about all that. Again, there's going to be another set of typewritten notes which should serve as a useful reference, but this gives us enough ammunition to then imagine that water molecules are just collections of dipoles and ions are just point charges. We can now work out some simple statements about how ions are solvated by a collection of dipoles like that of water.